I think it's time to start. Welcome back, everybody. Nice to see you all again. And for the first time, some of you. This is Point Set Topology. I said on the syllabus, Point Set Topology for Julias. There are 8 students in this class and 4 Julias. Can you believe it? That's amazing. So I'm going to try and, not exclusive to the non-Julias, but try and include some Julia-specific content whenever we can. There actually is a thing in topology called the Julia set. I don't know if you've ever heard. It's related to fractals. We will not be talking about the Julia set, though. So this is Point Set Topology. I'm looking forward to this class. This is the first time that I've taught this. 3385. I hope that you can all see the screens all right. I'm going to do everything on the screens because I like to record the class, and then I'm going to I'll post the videos after the fact so that you can watch it again if you are interested or if you miss class or whatever. Yeah, I have not taught this course before, although my research, my mathematical upbringing is in topology. That's kind of my thing that I do in my spare time. But because for whatever reason, Sean Rafalski is also a topologist, and he has always taught this course in the past, and I have never tried to fight him for it. But he is on sabbatical this semester, and so it has been entrusted to me, and I'm looking forward to it. Let's just talk briefly about the syllabus, and then we can, get down to some topology. So this is Point Set Topology for Julias. You can see my email address there is probably the best way to get in touch with me. My office is right in that corner on this floor. My office hours are written on there. Those are times when I will definitely be sitting in my office waiting to talk to you. If those times are not good for you, then please let me know and we can set something else up. You can come to my office for that, or you can connect by Zoom if you prefer. By the way, I'm wearing a mask today because one of my kids has COVID. I usually am not going to, but I'm feeling fine at this point. Well, thank you, Tessa. I think 2 of you actually have taken a class with me 3 semesters in a row. So thank you for coming back. Repeat customers. You can see the final exam date there, Friday, May 5th at 11:30. So put that on your calculator. This is the textbook, Introduction to Topology, Pure and Applied. I hope that, were you able to see that this was indeed the textbook for this class? No? Yes? All right, well, it is. There was some kind of mix-up with the scheduling. Like I found out very recently that I was going to be teaching this class, and so I was not entirely sure that the textbook was properly communicated to you all. But anyway, this is it. This is the one that Professor Rafalski uses. I found out very recently, like a few days ago, that it's pretty expensive. So I apologize for that. I try not to choose books that are super expensive. This one is kind of expensive. Sean likes it because, I think it's a good book. I mean, I've looked through it. The first author, Colin Adams, is a friend of Sean Rafalski's. Maybe there's some kind of financial arrangement happening there. I don't know. Anyway, that's the textbook. For the most part, the textbook will just be using for the homework assignments. So if you do feel like it's like too expensive, if you have a friend with it, then that will probably work out fine for you. All right. We have on here, you can see this code to get to the class website. You will want to visit that every so often because that's where I'm going to post the homework assignments and other things. The links to the videos that I'm recording will be on there also. So check that out. I do not use Blackboard. I just use this site because I like for it to be available, not like behind a login. So anyway, it's not on Blackboard. It's on that website right there. All right. Any basic questions about that stuff? All right. The course description. Here's what it says. This is the official description from the book. The course considers topological spaces, continuous functions, product, metric, and quotient spaces, countability and separation axioms, existence and extension of continuous functions, compactification, metrization theorems, and complete metric spaces. So this is what the class is about. I don't know if that makes any sense to you, but I'm going to try to talk today about sort of what is topology all about, because it's something that is not, I mean, if you meet like an ordinary person in public, they are not going to know what topology is at all. So I don't expect you to know either, and we'll try to get it across today. The exams there, you can see 2 midterms on, I have a typo in mine, but I fixed it on yours. There are 2 Fridays during the semester, so make sure you're there on those 2 days. It says no calculators on the exams. This really is not the kind of class where you want a calculator anyway, so don't worry about that. The final exam is cumulative. The midterm exams will not be. And then we have homework. These are like the 2 parts of your grade, is the exams and the homework. So it says the homework will be due on Wednesdays at midnight. You're going to submit the homeworks on Gradescope. No homework due tomorrow, but probably next week we will have some homework problems to do. All right? I'm going to post the assignments at the class website, like I said. And it's going to be on Gradescope. I hope that you're familiar with Gradescope. It's an online homework submitting thing. If you look on the back, you can see the grading breakdown there. Homework is most of it. And then the 3 exams give you 35% total from the exams. And that's about all there is to say. There's a little note about my office hours, and that's just, I hope you will feel free to chat with me during office hours. You know, if you have questions about the homework, which I assume you all will from time to time, it is not a sign of weakness if you have to ask me questions. That's kind of part of the process, so I hope that you feel good about talking about the homework problems, talk before tests, whatever. All right? And there's a little note about the counseling services on campus. Perhaps you know, you can get free counseling services. Can you believe it? The word free, of course, is, you know, included with your outrageous tuition costs, but please check it out if you're interested. It is helpful. All right. Any questions about any of that? That's all kind of the business. No surprises, I would say. All right. Let's get down to it then. This clock is off by 12 minutes or so. It's not very convenient. I have my own clock up here that I'm looking at. If you see me looking at my phone, it's because it's the clock. All right, let's talk then about topology. So my goal is to give you a feel for what topology is all about within, you know, that's my goal for today. And then we can sort of, if there's time, we'll get started with it. But I would like to start off with a little lesson on talking about topology in the club. This is something that actually happens to me all the time when I'm in the club. I don't actually go in the club, but people ask me, you know, I say I'm a mathematician or I'm a math professor. Oftentimes that is enough for somebody to like stop talking to me, which is fine. That's their choice. But sometimes people, either to be polite or because they're actually interested, they say, "Oh, well, what kind of mathematics do you do?" And I say, "I do topology." And they say, "Oh, is that like about maps and something like that?" Because they are thinking of the word topography, which is a different word. So my answer is no, it's not about that. When someone asks me, what is topology about? Or like, what is that? Usually what I say, there's this, I don't know if you've experienced this. There's sort of there's kind of a negotiation that happens when I meet a person who wants to talk to me about math. Because certainly the way that I talk about math to another mathematician is very different from the way that I talk about math to like an ordinary person, just because I want to be understood and, you know, I want to try to have an actual conversation if I want to. So anyway, if someone asks me, what is topology all about? My first response is, topology is like, this is what I say. I've had this conversation many, many times. It's like a modern form of geometry. And often, this is sufficient for a person. They'll say, oh, all right, and then, we talk about something else. And that's great. To me, my goal when talking to ordinary people about mathematics is not actually to make them truly understand something. I want them to feel as though they've understood something so that, because it's not my job to teach everybody math in ordinary life, right? But when people talk to me, they want to feel like I've said something, and they want to feel like they understand me, even though this, to me, is not a description of anything, really. Like, sorry, I'm trying to make my chair go down. I'm not heavy enough. It's like a modern form of geometry, I say. And oftentimes, they're like, oh, yeah, all right, great. This is kind of like, saying, like, when a mommy and a daddy love each other very much, that's where a baby comes from. The point is not to actually explain something, but the person hopefully will say, oh, yeah, all right, I guess that makes sense, and then you talk about something else. So this oftentimes is good enough for somebody who doesn't really want to talk about it. Sometimes people say, like, oh, really, what do you mean? Like, what's modern about it, or what's different about this from ordinary geometry? So this is like the first level, right? And oftentimes people just, that's good enough, and that's great. The second level, the next amount of detail, if they say, like, what does that actually mean? Well, my next tactic, I say, this is like geometry, so this is getting closer to a real response. Like geometry, but without distances and angles. And this is actually something that even real mathematicians would recognize this as a real answer. It's like, and this is true. This is topology is kind of like geometry in the sense that it's sort of about shapes and things like that, but you never use concepts of distances and angles, or not never. But, I mean, you can if you want to, but that's not what it's about. It's about geometry, but it's not about distances or angles or straight things versus curved things or anything like that. Topology is not about that stuff. This also is a statement which sometimes is satisfactory to people. All right, it's like geometry, but you don't use distances and angles. Sometimes, if they want to take it to the next level, they will say, well, then what is it? Because actually, to an ordinary person, geometry is about distances and angles. So, like, what does that even mean? This is still, this is not a meaningless statement, but it really does not answer the question still. So, what does that actually mean? I would say, if I wanted to try to explain this a little bit more, it's like geometry of, I would say, rubbery shapes. This is another way of explaining. It's like, it's doing mathematics that's vaguely about shapes, but shapes which don't have a specific angles to them, or they're not necessarily flat, because it doesn't really matter if they're flat anymore. It's geometry about shapes which you imagine to be kind of squishy or made of rubber or something like that, where it's not important precisely what shape they are. What's important is more, something else about them, all right? It's like the geometry of rubbery shapes. And now I'm going to try to give you two major historical examples. So this, when I'm talking to actual people about this, I almost never get to this point, but some people in real life really are interested in mathematics. And these are two examples that I often tell people to get a feel for what even is a topology problem versus a geometry problem. Like, I'm sure you're all familiar with many geometry problems. Everything you do in trigonometry is kind of about angles and whatever, but what is an example of a problem which is topological but not geometric? So I'm going to give you two important historical examples. This first one is really something like the original topology problem. I don't really know if it's the original, but this, historically speaking, is one of the first examples of a famous problem which sort of it seems like a geometry problem, but people realize actually this is not about geometry, it's about topology, which didn't even exist at the time. This is studied by Euler in 1976. Sorry, what? 1736, not 19. Doesn't make any sense. 1736 by Euler, and maybe you've heard of this problem before. This is called the seven bridges. The seven bridges of Königsberg, which was a city. And here's the idea. This is a real place that exists. There's sort of a river through the middle of the city. All of this is a river which has two islands in it. This is all water, which I will indicate by blue. And there are bridges. There are seven bridges. So there's land at the top, land at the bottom. There's a river and then two islands in the middle. And the islands are connected by bridges like this. There's one here. There's one here. One here. There's two here and two here. All right. This is a real place. You can go there. It's not. Apparently, the bridges don't look like this anymore. Some of them are gone, and there's other ones, but whatever. This was a real place. And the mathematical question is, can you walk across each bridge without repeating any? You want to go across each bridge once without making any repetitions of a bridge. All right? So this is, if you show this to anybody and ask them, like, what kind of a math problem is this? I would say it's like geometric because it's about a shape. It's not about calculus or numbers or whatever. But it's not really geometric in the traditional sense, in that, for example, I drew this bridge right here as more or less a straight line, but this one has a little bend to it. Huh? I don't know, did any of you notice that? Probably not, because it doesn't matter. In this problem, like, the point of this problem really has nothing to do with the precise shapes of the bridges, or the fact that, for instance, this island, the way that I drew it, it seems that this island is slightly bigger than this one. Does that matter? No. None of that really matters. In fact, anything that you would put under the category of geometry doesn't really matter in this problem. For instance, I drew it as if these bridges go at right angles with each other. That also is irrelevant, all right? So this, I would say, looks like geometry, but it's not. Right? Then what is it? Well, it's topology. That's what topology is all about. It's about handling questions like this. It is questions where it is vaguely about shapes, but I said you don't use distances or angles. It's not that I'm trying to do things tying my hands behind my back, like I'm not even going to use angles to solve this as a flex. No, it's just that angles have nothing to do with this problem. There's no, if you want to talk about distances and angles, they are irrelevant in this setting. Euler sort of figured out the solution to this problem. So the simple way to try to solve this problem is just to try it out. Like, maybe you've been doing this in your head as I've been talking here. Can you try and do it? You will eventually decide you probably can't. So the answer to this question, can you walk across each bridge? The answer is no, you can't. But of course, it's not good enough to just say, well, I tried it a bunch of different ways and none of them worked. That doesn't mean that it's impossible. That just means you failed to do it. So Euler was able to prove that it's impossible by realizing that this is not a geometry problem, it's a topology problem instead. So Euler's strategy, and I'm not going to get into the details of exactly how this works, but Euler's idea was just simply to realize, first of all, that nothing about that picture really matters except for where are the land masses and where do the bridges go? That's the only thing that's relevant. How long the bridges are, what shape the bridges have, it doesn't matter. It's just where are the places you can go and how are they connected to one another. And Euler distilled this whole picture into, there's basically the two islands, there's the land on the top and the land on the bottom. And that's all that matters. So it turns this into a picture like this. There are the two islands on the two sides. There's the land on the top and the land on the bottom, and they are connected by bridges in this way. There's a bridge here, there's a one here, here. So this represents the top, the bottom, and these are the two islands on the side, right? And then there's two here and two here. Euler's idea is to just throw away the geometry entirely and consider only this little diagram, which we now call a graph. Euler sort of invented graph theory in order to solve this problem. All that matters are the points. In this case, there are just 4 points that really matter, and the connections between them. All right? So sometimes when people want to talk about topology, they say it's kind of like geometry in that you are studying shapes, but you don't actually care about the specific shape. You care about how the shape is sort of connected with itself and with other shapes, perhaps. You do care about something like if the shape has a hole in it. That is important topologically, but you don't care about exactly what the hole looks like. If it's like a circular hole or a square hole, that doesn't matter. It's just what matters are the points and the connections, all right? And then Euler kind of invented a whole bunch of techniques to handle diagrams like this, which I don't want to get into, but this is the first example historically of a famous problem which we now see was not geometrical, but it was a topological problem, all right? Any thoughts about that? Have you seen this problem before? Maybe if you did some graph theory in like a discrete math class, sometimes this is something you discuss. I got one more historical example. Actually, when I'm talking to somebody in the club or whatever, I don't talk about this example if they really want to know, because this one you kind of have to draw the picture. But here's another one that you can try on your friends, talk to your friends at lunch about. This is a problem which I find is interesting to a lot of people. I mean, some people are just not interested in anything like this, and that's fine. But my other historical example is called the 4-color problem, or it's now called the 4-color theorem. It was an unsolved problem for a long time until somebody proved the 4-color theorem. But this is about maps, actually. So the people who think topology is about maps, I always say, no, that's topography. But actually, this problem is actually about maps. Anyway, if you imagine you have a map, like a map of the United States or something, just any kind of in a plane divided into a bunch of regions. So I'm gonna draw a specific map here. But the point of this problem is this is a fact about any map you can draw. I want to get it right. How about that? All right. So any planar map which is divided into regions, and let's just assume that there's no point in the map where 4 or more regions meet, and I drew this to have that property. Any planar map, no 4-way intersections. You allow 3-way intersections, there has to be, but no 4-way intersections. And we want to color the regions just like an ordinary map, which is divided into regions. Usually they're colored in such a way that no 2 neighboring regions have the same color. So we want to color it so that no neighbors have the same color. All right, so how many colors do you need in order to make that happen? Well, in this example, I have 1, 2, 3, 4, 5, 6, 7, 8. I have 9 regions total. So certainly, if you let me use 9 different colors, I could easily color them all so that no two neighbors have the same color. But you don't actually need 9 different colors in this example. For instance, I could make this one the same as this one over here because they don't touch each other, so I can reuse that color. I think actually, how many colors do we need here? I can do it with 3 colors, I think is possible in this example. Now I have this fancy pen which can do any colors, but maybe instead of actually making colors, just because some of you don't have colors, can I just put numbers here? These numbers are like colors. So that region I color number 1, up there I color number 2. This one I do a 3. I can make this a 1. I'm trying to do this so that, actually I changed my mind. I don't think I can do it with 3. I can do it with 4. Sorry. The picture I drew on here is slightly different from the one I drew on my paper, that's why. Anyway, if I make this a 2, this a 4, this a 1, a 3, and a 4. There, I did it. All right. Every region has its own color, and no two neighboring regions have the same color. I think I did it with 4. All right. Yes?
You do it with 3?
Could I? Do you think so?
Yeah, like if
I'm
you
interested.
make the bottom 4 a 1, and then the rightmost one a 2, and then the
Oh yeah, I think like that.
Yeah.
Yes. I don't know why I didn't like that when I was doing it before, but yeah, I agree. That's great. So in this example, I can do it with 3. Thank you. Thank you, Julia. Even if I have a hard time remembering some of the names, it's a good bet. I do know who the Julias are, but I probably will mix up your last names. Sorry. I just won't use your last names. All right. Now, there are some examples where you need 4, though. Can you think of a way to make an example where you absolutely have to have 4? I didn't in this case, but actually I can think of a modification. One scenario in which you might think I'm going to need a lot of colors is something like if you have one region here and then a whole lot bordering that same region, right? Now, you don't actually need all different colors here because I can go, say, 1 here and then 2, 3, 2, 3, 2, 3. So actually, this is going to work fine, right? Actually, it's not because I ended up with 2 2s next to each other, and that's not allowed. Actually, I could change this to a 3, but then I'd mess up that. So actually, this one right here requires 4 colors because by the time you make it all the way around, you have run out of colors. Here's a simple one, a simpler one, which I think is clearer. Something like that. Here I have 4 different regions, and actually every one of the 4 touches all of the other ones. So certainly you're going to have to use all 4 have to be different colors here, because I have 4 regions, and each of the 4 regions touches one of the other 4. So there's no way to do that one with less than 4. All right. So I want to say sometimes 4 colors are required. All right. But is there any example where 5 are required? And actually, this is the big question. So this is what was known as the 4-color problem. And this was first posed, I believe, I looked this up, in 1852. This was not posed by a famous mathematician. This was some kind of like write-in fun math problems section in a newspaper or something where people could like submit their own whiz-bang problems, and this was one of them. Nobody thought that it would be a major thing, but it turned out to be much harder than anybody thought. And anyway, the 4-color problem just says, are 4 colors enough for any map? Sometimes you do need 4, but could you color in any map with 4? Or is there some kind of map in which you need 5? All right. Again, this is an example of something which seems to be a geometry problem, but really it's a topology problem because, like I said before, when you look at these pictures here, there are certain shapes that I'm using, like this one is a circle and this one is a rectangle, but really that doesn't matter. What matters is what are the shapes and how are they connected with one another. That's the only thing that matters. The specific geometry of these shapes is irrelevant, all right? That's what makes this a topology problem. And this is, I think, part of what made this such a hard problem for people to approach, because topology as a discipline didn't really exist in a formal way before the 20th century. And so when this problem arose around this time, there really were not, people didn't know how to do topology problems really, just because topology didn't really exist in the way that we now think of it. All right. Anyway, there's an interesting story behind the solution of this problem. This was eventually proved that actually 4 colors are enough, no matter what the map looks like. So eventually it was proved that 4 colors suffice. And it was actually, the proof was published in a book called 4 Colors Suffice. I believe that was the title, or maybe the title of an article. 4 colors suffice. It was proved in 1976. So this was an unsolved problem for a very long time. And by this time, it had become such a famous thing that it was like you are going to be a big shot if you can actually prove this. And it was actually, there were many different bad proofs, and there were some wrong proofs that had been published and were accepted for decades until it was eventually found that they were wrong. And so even in 1976, there was a lot of skepticism about this proof because people had been burned in the past. But it's now 50 years old or so, and we still believe it. There's something even more interesting about this proof that was done in 1976. This is actually one of the more interesting stories of 20th century mathematics, in my opinion. So the proof is famous. Actually, the theorem itself is not regarded as terribly important. Like it's not like that. Those 4 colors are like significant, or this doesn't allow you to prove other theorems. It was just kind of a curiosity, and it's still not really regarded as an important theorem to have a proof of. But the proof is kind of famous because it was done by a computer. This is the very early days of using computers in mathematics, and the first major example of a theorem which was proved with the help of computers. And the way that this proof worked was that these are 2 names. These are the people who, their name is on the proof, Haken and Appel. Haken is an otherwise famous topologist who is well known for other things, and he also is known for proving the 4-color theorem. Appel was kind of like the computer guy in this outfit. It was like Haken had this idea of how he could do the proof, and then apparently he found this other guy, Appel, and he's like, "Hey, you know computers, right, Appel?" And he was like, "Yeah, I guess." And he said, "Hey, do you think you can make a computer program to do this and this and this?" And they did it together. But anyway, Appel proved, so basically this part of the proof was done by hand by Haken. They proved that any map that you can draw, any map has a reduction, this is the terminology they used, a reduction to one of 1,834 specific configurations. This was Haken's big idea. Of course, what makes the problem hard is that the map could be anything. It could be drawn in any kind of crazy way. But Haken figured out how actually all of the possible maps that you could imagine, they all boil down into only a few cases, but a few meaning 1,834 different cases. And then each of those cases was checked on the computer. So this is like a big proof by cases, really big proof by cases. All right, so they proved by hand that any map has a reduction to one of these configurations, and then these were individually checked by the computer. So the computer, basically by brute force, actually drew a map of this configuration and then figured out how to draw the colors. So basically by guessing over and over again. So these were individually checked by the computer. By Apple's computer program. This was super controversial at the time. I don't know if you care about this history, but I think it's interesting. It was controversial at the time because it was really, a lot of people sort of referred to this as like the worst mathematical proof in history, because the whole point of doing a mathematical proof at all is to somehow like gain some more insight about the problem so that you can use your new knowledge to prove other things or to make other conjectures or whatever. This is a proof which, well, yes, it does establish that the theorem is true, but it provides no insight at all because no human being can actually read through the proof, and you can't like understand it in your mind fully. I think this part of it, just the reduction to the configurations, that is something that makes sense. But then actually checking all the configurations is just a bunch of nonsense. And they ended up publishing this in a big book, which is like many hundreds of pages, and basically every page looks the same. It's just another one of these specific examples that's worked out. And at the time, computers were not a big deal in society at large. And so actually Haken and Apple, and Haken somehow got his daughter involved in this. They actually looked through every page of the computer output to verify that it was correct. But this was deeply unsatisfying to a lot of people. And for a long time, people were sort of still looking for like the good proof of the four-color theorem, because this is not a good proof. And unfortunately, actually, there is still no good proof of the four-color theorem. So improvements since then, I will just say, there's still no short proof, or there's no proof that you can actually read and feel like you've understood something. You can read through the whole thing and decide that it's really true, but there's no good proof. So it has been improved a little bit. So the best modern proof, I just looked this up yesterday, uses 633 individual cases, which is better, I guess, but still not in the like acceptable range for people to feel good about the proof. All right. So it's definitely a true theorem, but it has a weird proof. All of this has nothing to do with topology, really. I just thought this is an interesting story about the four-color theorem. I actually know a guy. This is a very. I think about this often, actually. I know a guy who went to grad school where Haken and Apple were, and Haken came to my friend Larry, and Larry's much older than me, but we've done some research together. Haken came to my friend Larry and said, "Hey, you know about computers, right? Do you think you could write this program that does this and this and this?" And Larry, his response was like it sounded like a reasonable idea to him, but like he was really busy that week or something, and he was like, I don't think I can get involved with that. And so, Haken went to this other guy who's now like a famous guy, and has had an illustrious career, which Larry passed on. This is really, I feel bad for Larry. I'm sure Larry lives a fulfilling life, but always with the knowledge that he passed on this opportunity. Okay, anyway, I hope Larry is not watching this video on the YouTube. This is the end of my historical introduction. I'm trying to give you a feel for what counts as a topology problem versus a geometry problem. All right, topological problems involve sort of connectivity where things about geometry don't really matter. Topology is used a lot in the real world. Topology is the principal way that you want to analyze, for instance, a network of computers. If you have a bunch of computers that are connected to one another, of course, there is some geometry in the connections. Like if I plug my, when I'm sitting in my office, I plug my computer into the internet with an Ethernet wire, and the wire goes from the top of my desk where I plug it in, it goes kind of like down to the floor, and then the wire that I use is actually much longer than it has to be, so it has like a big spiral in it, and then it connects to a fiber optic router on the floor, and then that goes through the wall and somewhere else. You may be wondering, why am I explaining all of these details? They are totally irrelevant, and this is the point I'm trying to make. The fact that my wire goes in a spiral has nothing to do with anything. That's not important at all. So I will just say again what I said before. The proper way to analyze a computer network is not by using geometry, it's by using topology. All that matters is my computer is a thing somewhere and it's connected to this other computer or this other router or whatever it is. All right? Connections, it's all about connections. Okay, great. We have 10 minutes remaining. I wanted to try to get down to some real details here. Oh, I had one more thing. Maybe this won't take 10 minutes, but in topology, I meant to say this before, but I forgot. Well, can I say, here's another way to think about the difference between geometry and topology. In geometry, these shapes are all different. A circle is a very important shape in geometry, which is quite different from a triangle. Every kid knows a circle and a triangle are different, or a square, or even something like a star, right? These are all different geometrically, definitely different. But in topology, these are all regarded as the same. They're all sort of basically like the circle. If you consider them to be kind of wiggly or rubbery, they are all the same in topology. They're all the same. And if you understand this, then you can understand a hilarious math joke, which I have actually on my office door. I don't know if you've ever noticed this. If you pay attention to what you see on professors' office doors. This is a sign that's on my office door here. You get it? This is a topology joke because it's a circle right there. It's supposed to be like a heart, but to a topologist, the circle is the same as the heart, and so that's the joke. I have fully explained the joke now, and you can tell all your friends about this hilarious joke. This is an example of. This is on my door. I think it's kind of cute, but I'm also somewhat conflicted about math jokes in general. I feel like this is a joke. Part of the satisfaction of getting the joke is not just that it's actually funny, but also that you get to feel like you're smarter than everybody else because you understand it and you think my idiot brother would never understand that, but I do. I think math jokes they turn into some kind of like exclusivity badge or something. Like I feel good about myself because I understand. Anyway, that's the topology joke. All right, let's. We got a few minutes here. I want to start talking about topology specifically. So all of this stuff that I've been talking about shapes and connectivity, actually, we are not, the day-to-day workings of the class is not really going to look like that stuff at all. This is the way it goes sometimes in advanced math classes. The day-to-day workings of the topology that we're going to do is all about set theory. So we'll do lots of set theory proofs. And not everything is going to be a proof, but proofs and other kinds of things involving set theory. All right. I am often going to draw pictures, but they are meant to be sort of schematics, not specific pictures that are literally meaningful in the context of what we're talking about. So I thought it might be helpful for us to start with a little review of some set theory, just because it's going to be so super important for the rest of the semester. And I have a list of 5 little set theory proofs that I thought I was going to ask you all to try and work them out. Now, we don't have enough time to do all of them today. So maybe we'll just leave it at that for today, if that's all right. So